All right, so today we're going to begin the first part of the second module, which is probability. And as always, we're just going to start off with some basic definitions and terms. All right, so when we deal with probability, probability is just a measure of likelihood that is given that an event will occur, or sometimes a probability is a likelihood that an event will not occur. Okay, it all depends upon the setup on the problem. Probabilities are expressed as a number between 0 and 1. Now, as far as the numbers are concerned, every number can be represented as a decimal. Like, for example, 0 is technically written as 0.0, right, where the decimal lies beneath right after 0. And also 1, right? 1 as a decimal is written as 1.0, but that 0.0 is understood. You can convert numbers or decimals to percentages and vice versa. So 0 as a percent would be 0%. 1 as a percent would be 100%, right? So anytime you want to convert a decimal to a percentage, you simply move the decimal 2 places right, and add the percentage symbol. Okay, so for example, 1 is 1.0 as a decimal. If I were to convert that to a percentage, I would move the decimal 2 places to the right. I would add a 0. So therefore, 1 is equal to 100%. Okay. On some of these problems, they want you to enter the probability as a number, right? So as a number, it's going to lie between 0 and 1. As a percentage, it's going to lie between 0 and 100%. Okay. If you take a look at the first problem on the module 2 part 1 handout, it's a question that deals with just that. It says, which of the following values could not be a probability? I'm just going to bring up the calculator. All right, I'm just going to return to the home screen and clear that out a little bit. So we basically want to convert these numbers to percentages, all right, or probabilities. So it says, which of the following could not be a probability? So could 8 not be a probability? So remember, our probabilities are between 0 and 1, or 0% and 100%. So 8 would be an answer, right? 8 could not be a probability because it exceeds 1. A probability can never exceed 1, and a probability can never be negative. So 8 would count as a number that's not a probability. What about 6 over 7? Well, if we were to convert 6 over 7 to a number, if that number is in between 0 and 1, okay, so notice that this says 0.85. However, if we were to convert 0.85 to a percent, right, I would move my decimal 2 places to the right. So this would actually give us 85%. Okay, and then 0.8 is a number that's between 0 and 1. So 6 over 7 could actually be a probability. All right, so we're not going to count that. We're only considering numbers that are not probabilities. Okay, what about the third choice, negative 0.1611? Right. This is not a probability because it's negative, so that would constitute as an answer. What about the square root of 10? All right, so I'm going to analyze the square root of 10 in the calculator and just see if it is a value between 0 and 1. So notice that the square root of 10 is 3.1, which actually overshoots 1. So the square root of 10 could not be a probability. All right, so we'll accept that as an answer. And then the last one says the square root of 1 divided by 7. All right, so I'm going to put this in the calculator. The square root, okay, 1 divided by 7. I'm going to close my square root function. And then if I hit enter, since it's in between 0 and 1, this would be a probability. So to answer these questions, 8, negative 0.1611, and a square root of 10 are all of the following that could not be probabilities. So when you're answering these type of questions, just be mindful of what it's asking you. This particular question is asking which cannot be a probability. Okay, so that's the very first thing about probability. It ranges between 0 and 1, or 0% and 100%. Now here's some notations for probability. Whenever you see P, that denotes a probability. A, B, and C, they denote specific events, and those events will be given to you in the problems. Right? So when you see this notation, P of A, that's just denotes the probability that event A is occurring. Okay? So just a little bit of probability notation. Okay, going to the next slide. This is a classical approach to probability, right, which is more so like a fraction. If you think about a fraction is a part over the whole. Classical probability and even percentages operate in the same manner. So it says assume that a given procedure has n different simple events, right? So if I'm looking at a fraction, or if I'm looking at this probability formula, the denominator is the number of specific events. That would be like your whole. The numerator is if each event A occurs in S in n ways, this is our probability. So the numerator would be the number of ways that an event can occur. That would be your part. And then the denominator would be the number of different simple events. Or as far as a fraction, that would be all of the total possible events. Okay, so we want to take the part of the events that we care about, and we want to divide that by the total number of events. Now there is an example. Okay, that's on the notes. It's also number 4 on the handout. All right. Okay, so number 4 on the handout is the exact same problem as that example. So here's an example that uses the classical approach to probability. And in this question, it says, in a study of brand recognition, 1,001 customers knew of McDonald's, and 32 people never heard of McDonald's. Use these results to estimate the probability that a randomly selected customer will recognize McDonald's. Right? And we're asked to answer as a fraction rounded to 3 decimal places. So we want to find the probability that a randomly selected consumer will recognize McDonald's. Okay, so I'm just kind of writing this out in a probability format. All right. So what's that probability? Well, if you think about the classical approach to probability, or more so even thinking about a fraction, right? The first thing I would fill out is the denominator. So in this case, the denominator would be the total of consumers. So if I look at the total, right, I had 1,001 consumers that knew McDonald's, 32 that didn't. If I were to add those two together, 1,001 plus 32, I'm going to get what? 1,033, right? So that's all of the people in the study, right? That's the whole, everything. The part that we're interested in is the consumers that will recognize McDonald's, right? So if I look back at my problem, it says 1,001 knew of McDonald's, right? So that's the part that I'm interested in. So that's our numerator. All right, so I'm going to write that in as 1,001. Okay, divided by 1,033. Okay, is everybody okay with that fraction? Right, so we're taking the part that we're interested in, which is the 1,001 people that knew of McDonald's, and we're dividing that by all of the consumers in the study. All right, so if we divide that up, 1,001 divided by 1,033, we get, and it says round to 3 decimal places, 0.969. So since I'm rounding to 3 decimal places, I'm just going to locate that third decimal place. I'm going to look 1 decimal place to the right. And if that decimal place is 5 or less, or 4 or less, we're going to remain this as a 9. Right? So we have 0.969. If you wanted to convert this to a percentage, right? So notice I rounded my number to the intended decimal place. In order to change this decimal to a percent, I would move that decimal 2 places to the right. So this would be the same as 96.9%. So notice when you're asked to round the 3 decimal places, some of the problems ask you to round, and they ask you to express it as a decimal. Others are going to say round the percentage to the nearest place. So notice you round the number first, and then you move that decimal 2 places to the right and add your percent. So 96.9% means that there are quite a few people who are going to recognize McDonald's, right? The closer you are to 1, the more likely it is that the event will happen. All right. All right, so let's go back to the lecture notes. All right, and we're going to talk about independent and dependent events. A dependent event is an event that happens, but it happens only if something before it happens, right? So here's an example. The event of having your car start and the event of getting to your statistics class on time are dependent events, right? Because you could, depending on your car to start versus, you're dependent on your car to start, and that's going to in turn affect when you arrive in class, right? So your car starting is dependent upon you arriving to class. Okay? So that's a dependent event. One outcome has the effect on the probability of another outcome. So those are dependent, and we're going to take a look at some examples of the dependence. Next, we have independent events. And independent events occur when one event does not affect the other event. And here's an example, and it says playing the New York lottery and playing the California lottery are independent events because the events of the California lottery has absolutely no effect on the outcomes of the New York lottery. Okay, now as far as the lottery is concerned, I have a friend of mine who plays the lottery quite religiously. So he asked me one day, he said, well, these numbers hadn't failed yet. So he just wrote some numbers down and he said they hadn't failed yet. So I'm going to play these because they're going to fall. So I told him that each draw is independent. So it's almost like when you see the lottery and the balls coming out of the machine, it's basically like each lottery draw is like starting all over, because one event or one draw doesn't depend on the other draws. And then he come to realize that, and this wasn't me saying this, it was just all of this statistic stuff, that it doesn't matter if the numbers have failed yet or not, since each draw is independent of the other. It's impossible to say, well, these numbers are going to fall because they haven't failed yet, right? So it's like each time you see the lottery and each time the number is drawn, it's just like it's starting over because nothing is dependent. All right, so that's an example of independent events. Okay, next we're going to talk about the fundamental rule of counting, and then we're going to take a look at some examples. So here is the fundamental counting rule or the fundamental counting principle. It says for a sequence of 2 events, but this should actually read for a sequence of 2 or more events, because we're going to see this thing expanded out to more than just 2 events, in which the first event can occur M ways, the second event can occur N ways. The events together can occur a total of M times N ways. The fundamental principle of the fundamental counting rule easily extends to situations involving more than 2 events, okay, as illustrated in this following example. So this is an example dealing with license plates. And it says license plates in Wyoming consist of 2 letters followed by 4 digits. How many different license plates are possible in Wyoming? And we're going to use the fundamental principle of counting to determine that. Okay. So it says 2 letters followed by 4 digits. And this is one I got to copy over. So give me 1 second, I'm going to copy this example. Okay, that's what I did wrong. All right, so here it is. So we're going to use the fundamental principle of counting to figure out how many license plates. All right, so now one thing about this is not asking for a probability. Like a probability would be a percentage between like 0 and 100%, right? This is not asking for that. This is asking for how many different license plates. So keep that in mind. So we have 2 letters followed by 4 numbers. So I'm going to draw out 6 spaces. 1, 2, and I'm putting that multiplication dot. Right, so those are the 2 letters and 4 numbers. So I have a total of 6 events, right? So the fundamental principle of counting says 2 or more events. So let's look at the first blank in the license plate, and that would be a letter, right? So how many choices of letters do you have? 26, right? So there's 26 different letters to choose from. For the second spot in the license plate is also a what? Letter. So again, that's going to be 26 letters to choose from. So notice I'm multiplying. So in between each one of these blanks is a multiplication dot. And then it's followed by 4 numbers. So for the third character in the license plate, which is a number, how many numbers are there to choose from? 10, right? So it's 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 0 through 9. So we're not counting 10 as a number. There's 0 through 9, which constitute 10 numbers to choose from. All right, so that's 10. The next choice is 10. Okay, also the last 4, since there's 10 numbers, right, 0 through 9, there's 10 choices for numbers. So now in order to find up the different possible combinations, I'm going to multiply all these things together. So if I like to write this out in a scientific or exponential form, it will be 26 squared times 10 to the 4th power right? So I'll just do it both ways. So 26 times 26 times 1, 2, 3, 4, which would be 6,760,000. 6,760,000 possible license plate combinations. So I just kind of did it the first one. I just put all of the numbers in. Or you can put in 26 squared times 10 to the 4th. So 26 squared times 10. And if you want to raise 10 to the 4th power, you want to use the caret, right? That's what that's called, a caret, to the 4th power, and you should also get that same value. This works with a lot of things. It works with Social Security numbers, right? Everybody in here has a Social Security number that has, what, 9 numbers in it. So I'm going to just write it. So how many possible Social Security numbers and I'm going to say for South Carolina. Now, in your Social Security number, the first 3 numbers, that tells where you were born. Like my first 3 are 256. That means Georgia. They have some other ones now. Like my daughter's, her first 3 are like different than mine. But the first 3 kind of designate where you were born. I think your race is in there. Your age is in there. There's a lot of stuff in those numbers that you see. So like if I were to say the possible Social Security numbers for South Carolina, right? Let's see. So that's going to be, I'm going to draw out 9 blanks. 1, 2, 3, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6. All right. So now as far as the Social Security numbers are concerned, since this is South Carolina, the first 3 numbers are going to be like limited on what you can use, right? So without asking anybody if there's like Social Security numbers or anything, I'm going to pull up Google
So when we're writing these out, like if it was something like some crazy number possibility, we just basically put like the possible numbers to the whatever power.
Well, no. It wants you to write out a physical
So we just have to
number.
write it.
That's
Okay.
right. That's right. That's right. So beginning. So the meaning of Social Security number. So now this says that if you're South Carolina, it ranges from 237 to 246. Well, no, that's North Carolina. South Carolina is 247 to 251. So now if you're doing this specifically for South Carolina, how many choices for your first digit would you have? It would be 1, right? Because it has to be a 2. I'm just basing it on this Google thing. The first number has to be a 2. So I don't have 10 numbers to choose from. I only have 1, which is a 2. So I'm going to go back to OneNote, and there is only one number I can use, right, which is a 2. The second number in a Social Security number for South Carolina can either be 4 or 5. So how many choices of numbers do I have for the second number in a Social Security number for South Carolina? 2. It's either 4 or 5. What about the third number? Oops. Come on. It says 247 to 251. So how many numbers can I have for the last spot? Well, you can have 247, so I got a 7. I could have 248, so I could have an 8. I could have 249. I could have 250, and I could have 251. So that's only 5 numbers I can possibly choose for the third digit, right? So that is a 5. Okay, now what about the rest? All right, so for the rest of them, I could have possible 10 numbers to choose from, right? So this is the reason why, since I was kind of narrowing this down for South Carolina, it's not just 10s all the way across. You have to keep into mind the numbers that you can and cannot use, all right? So if I put 10, and then if I multiply all this stuff up, we should get 1, 2, 3, 4, 5, 6. 1 times 2 times 5 times 10 to the 6, which is actually 10 times 10 to the 6, which is actually 10 to the 7th power. So however you want to simplify this up, there are a total of, is that 10 million? 10 million Social Security numbers for South Carolina now. All right, so notice that this fundamental principle of accounting, it does not give you a probability value. It only gives you the number of items to choose from. Okay. All right, now we're going to put all of this stuff together in a problem or in some problems. So we're going to look at problems 5, 6, 7, 8, and 9 on the handout. All right, so let's look at problem number 5. All right. It says a study reports that 70% of all the people own cars. All right, so notice that this says all the people. So this would be a parameter statistics about a population. Okay, so it's not saying that a sample of, 30 people were taken. and 70% from that sample of 30. This says that all people who own cars was 70%. Suppose that 3 people are chosen at random from this population. Answer the following questions either using a fraction or a decimal rounded to 3 places. Are the events dependent or independent? So what they mean by that is you have a population of people, all right, let's say everybody in the United States, and you choose 3 people at random. So I don't necessarily think you're going to take 3 people like in a close vicinity or anything like that. Are those 3 people that you choose, are they dependent or are they independent? Now, if it's a large population of people, I doubt very highly if the 3 people know each other at all, right? Because you're dealing with a population, and anytime you see a population, you're dealing with a large group of people, right? So the events would be independent, right? Because choosing one person has no bearing on, well, one person says has no bearing on what the other person says about owning a car. So it will be independent. B says why. So it's actually like some answer choices. It says the people are chosen with replacement. The people are chosen without replacement. There are many kinds of cars. A sample is provided. But the answer is the events derive from a large population, right? Since the events derive from a large population, as I said earlier, what one person says about owning a car has nothing to do with what the next person says about owning a car. Okay, so these events are independent, and the reason is they derive from a large group of people. Okay? So there's no relation between one and the other. C says, what is the probability that they all 3 own a car? Right? So I'm going to use the fundamental principle of counting. So even though this says what is the probability, the fundamental principle of counting comes in when we have 3 people that we're choosing answers from. All right, so this first blank would be the probability that the first person you chose owns a car. The second blank is the probability the second person you choose owns a car. And the third blank is the probability that the third person you choose owns a car. Right? So I'm just mapping this out with 3 places, right, which represents the 3 people that we choose at random. Okay. So now for the probability, what's the probability that the first person we choose owns a car? Well, if I go back to the top, it says a study reports that 70% of all people own cars. So the probability that that first person owns a car is what? 70%. Right. So I'm going to write that as a decimal as 0.7. Okay. So now when you change a percent to a decimal, you reverse the process. You remove the percent and you move the decimal 2 places to the left. To change a decimal to a percent, drop the percent sign and move the decimal 2 places left. Okay, so for example, 70%, if I were to move the percent symbol, I have 70, right? And that decimal is understood to be behind that last 0. And then I would move my decimal once, 2 places to the left, so that becomes 0.7. So when you perform your calculations, you have to convert those percentages to number values, right? So 0.7 is the probability that the first person owns a car. What's the probability that the second person owns a car? Well, it's going to be that same 70%, right? So that's 0.7. And the probability that the third person owns a car would also be what? 0.7. So that percentage was given, 70%. We just simply had to use the fundamental principle of counting with 3 people. So now in order to get the probability that all 3 own a car, I'm simply going to multiply. So that's 0.7 to the third power, which is, right. So I can just punch in 0.7 times 0.7 times 0.7, or I could put it in as 0.7 raised to the third power, and we get 0.343, which would be 34.3%. Okay. All right. So this doesn't specifically tell us if they want a decimal or percentage. Okay, so I'm just converting both ways. All right. Any questions about that example? Number 5 is independent. One probability, one person or one outcome doesn't affect the other.
Would it be better to write it as a percent because it gave us a percent in the beginning?
The beginning, that's right.
Okay.
Now, they'll be more specific in the homework.
Okay.
For these examples, they don't really tell us to, well, let's say the answer as a fraction or a decimal. So I guess you would use 0.343. Okay. But I'm sort of doing them both ways just in case the problem states something different that you're working with. All right, let's look at number 6. And number 6 says, I want to move that down a little bit. A jar contains 10 orange marbles, 12 red marbles. If you reach in the jar and pull out 2 marbles at random at a time, so that means you got them in a jar, you're shaking them up, and you're pulling out 2 together at the same time. So you're not pulling one and then pulling another one. Okay, you pull 2 out at the same time. All right. Answer the following questions. Are these events dependent or independent? Well, now, if I was pulling, okay, so you have these scenarios. You have something that's called with replacement and without replacement. So with replacement means if I were to pick one marble, look at it, put it back, that's with replacement, shake it up, whatever, and pick out another marble. That would be independent. That's with replacement. Then you have something that's without replacement, which is sort of this example. You reach in, you grab a marble. That marble is here. So you've taken away from the total population of marbles. And then you reach in and pick another marble. Now you're still holding this marble over here, so that's going to have some effect on the probability for the second marble you pull, because you're not putting it back and starting from a total pot. So this would actually be a dependent. Okay, so we hadn't talked about with replacement or without replacement, but this would be an example of without replacement, because we're taking 2 marbles at a time. So technically, the first marble our hand touches and keeps, that affects the probability for the second marble, because we've taken that first marble out of the original sample. Okay. So those events would be dependent. And this is the reason why. Okay, it says why select an answer. The marbles are drawn from the jar with a large number of marbles. That's not true. Each marble is replaced before the next marble is drawn. Okay, that's the replacement deal. And if that were the case, it would be independent. The second says the total number of marbles is known. I mean, that's true, but that doesn't quite answer the fact that if it's dependent or not. But this third choice, the marbles are chosen at the same time. That's what makes it dependent. Okay, dependent probability. All right. So this was actually called without replacement. So now it says find the probability that both marbles are orange. So we're taking 2 marbles out at a time, and we want the probability that both marbles are orange. So this is asking me for a probability, but I'm going to use that fundamental principle of counting. Because we're going to determine, we're choosing 2 marbles, right? We're going to take a look at the probability for both. Okay. All right, so now we're dealing with probability, and they have not given us like 70% or 30% or anything like that. So let's take these one at a time. What's the probability of choosing an orange marble? So remember our fractional definition or the classical approach to probability? We want to take the number of orange marbles, right? That's the part we're interested in. And we want to divide by all of the marbles that we're choosing from. So first I'm going to start with the denominator. How many marbles do we have to choose from? Well, there are 10 orange and 12 red, so that's a total of 22 marbles, right? That's all of the marbles, that's the base, that's the whole. In the numerator, we want the number of marbles that are orange. So that's 10, right? So is everybody okay with that first probability, 10 out of 22? What about the second probability? So keep in mind now, we've already taken an orange marble out, right? So that would make the top 9. So there's a total of 9 marbles to choose from now. What about the denominator? We no longer have 22 marbles, right? Because we took 1 out. So we now have how many marbles? 21. So is everybody okay with the percentages? Okay, 10 out of 22. Because the first marble that we chose was orange. There were 10. And there were 22 total. The probability for the second marble being orange, we've taken 1 marble away, so the denominator now becomes 21 because we've taken 1 out. And now we no longer have 10 orange marbles because we've chosen 1. We now have 9. In order to calculate the probability, whenever you multiply fractions, you multiply the numerators, multiply the denominators, and simplify. So for my numerator, I'm going to have 10 times 9. The denominator is 22 times 21. So 10 times 9 is 90. 22 times 21 is 462. I'm going to divide this up. 90 divided by 462. And we are to round to 3 decimal places. So 4 is in the 3rd decimal place. I look 1 number to the right. Since that number is 5 or higher, I'm going to round 4 up to 5. So we should have 0.195, right, which is 19.5%. So any questions about number 6? So, okay, everybody.
So when it's a dependent problem, like a good rule of thumb is to always take 1 or whatever the number is.
Right,
now.
right, right.
Dependent.
That's right. So notice in the first problem, since it was independent, all of the percentages or probabilities had the exact same probability. Right? But for the second one, we drew 2 at a time, so that was the dependent event. So we had to make sure that we accounted for, in this case, an orange marble being taken away from the total that we started with. All right, now numbers. I would like for you to do number 7 and number 8, and then we'll kind of take a look at them in class. Number 7 says a die is rolled twice. So die is singular, dice is plural. So you're taking a 6-sided dice, because normally in this class, if it doesn't tell you how many sides it has, they're using a standard 6-sided dice. But there are some examples where they use like an 8-sided dice. So it says a die is rolled twice. So you roll it once, note the outcome, you roll it again, note the outcome. What is the probability that a 1 on the first roll and an odd number on the second roll? So just as a heads up, this one is going to be independent, because one roll of the dice, unless you got a trick dice or something, doesn't have anything to do with your second roll. So you need to find a probability of rolling a 1 and then find a probability of rolling an odd number. All right, and you use that fundamental principle of counting. B says Ethan has a bag of pencils with 6 white, 11 yellow, 5 blue pencils. Find the following probabilities. Ethan drawing the given pencils from the bag if each pencil is removed from the bag after it's drawn. So that's that without replacement. So sort of like that marble, that's a dependent type probability. So then it wants you to find that the probability of pulling a white pencil, then a yellow pencil, the probability of a blue pencil, then another blue pencil, then the probability of a white, then another white, and then a yellow. All right, so I'll give you about 10 minutes or so to answer these problems, and then we'll take a look at them together as a class. All right, so let's take a look at number 7. Okay, so it says a 6-sided die is rolled twice. What is the probability of rolling a 1 on the first roll and an odd number on the second roll? So we take a look at the first roll, right? There's 6 sides on the dice, so my denominator was 6. There's 6 numbers to choose from. I'm only interested in the number 1, so the probability of rolling a 1 would be 1 out of 6, right? For my second roll, I want the roll an odd number. Okay, so for my second probability, there's still 6 numbers to choose from. How many odd numbers are there? 3, right? There's 1, 3, and 5. So there's 3 odd numbers, right? So we're going to calculate the probability. So we're going to multiply the numerators. So 1 times 3 is 3. 6 times 6 is 36. We can reduce that, right? 3 divided by 36 is 1/12, right? So it would accept 1/12 as a fraction. But if we were to write it out as a decimal, I'm just going to divide that up real quick. We would get 0.83 as a decimal. I'm sorry, 0.083. So now I'm just going to ask this question. Does it seem very likely that you're going to do this? No, right? Because if I were to change 0.083 to a percent, I would move that decimal once, twice to the right. So there's like an 8.3% chance. And the further you are away from 1, the less likely it is that that event will happen. Okay, so that's I would say highly unlikely. Not to say it can't happen, but with 8%, that's a highly unlikely event. And that is an example of independence. Okay, for 8, this is a little bit different, similar to the marble example. Right, so it says Ethan has a bag of pencils, 6 white, 11 yellow, and 5 blue pencils. So how many pencils do we have all together in the bag? Right, 22, right? So N is going to equal to 22. So for this first one, it says, okay, and it says that each pencil is removed from the bag after it's drawn. So once you take a pencil out of the bag, you're not putting it back in the bag. So it says a white and then a yellow. All right. So we're going to use the fundamental principle of counting. So since we're choosing 2 pencils, right, we're listing 2 outcomes. So what would be the probability that the first pencil you choose is a white pencil? Right. Well, we're going to set up the probability for choosing a white pencil with the classical approach, right? So how many pencils are there together to choose from? 22, right? That's the denominator. How many white pencils? 6. Okay. All right, so we're taking 1 pencil from the bag. We're not placing it back in. So now on our second choice of pencils, how many are there to choose from? 21, right? How many yellow pencils are there to choose from? 11, right? Okay. Now, since the first pencil was white, that doesn't affect the number of yellow pencils still in there. There's still 11 yellow pencils, but there are only 21 pencils now since we've removed 1. So that's 11 over 21. So to calculate this probability, 6 times 11 is 66. 22 times 21 is 462. 22 times 21, 462. And they want us to answer it as a fraction or a decimal. So just one thing, if you're answering it as a fraction, you want to make sure that your fraction is in lowest terms, okay? So now you can actually force your calculator to do it, and I'll just show you how. So if I were to divide 66 by 20, 462, and if we were to round to 3 decimal places, we should have 0.143. Now I can, from this point, I can see if my calculator will convert this to a simplified fraction. So the way I'm going to do that is, since I already have my fraction answer entered, I'm going to hit math, and the first option, it states that it'll take whatever it's given and it will attempt to write it as a fraction. So if I hit enter and enter again, it gives me 1/7. Sometimes it'll make a fraction and sometimes it won't make a fraction, right? But again, that's in the math function and it's that very first option. So 0.143 or 1/7. The second problem says the first pencil is blue and then the second pencil is blue. So here again, I'm going to map out two choices. All right, so we're going to set up our probabilities. So there are 22 pencils to choose from. There are 5 blue pencils. So the probability that my first pencil chosen is blue is 5/22. For my second choice of pencil, my denominator changes because we've already chosen 1 blue pencil. And it also reduces the number of blue pencils in the bag, right? So instead of being 5 blue pencils, they're going to be what? 4 blue pencils. Okay, so this is the dependence part of the probabilities. So we're going to multiply the numerators and the denominators. So we get 20/462. Right. I'm going to convert it to a decimal. 20 divided by 462. And if we express it as a decimal rounded to 3 places, we would have 0.043. If you wanted to answer it as a fraction, you just want to make sure that the fraction is in lowest form. So I'm going to hit math. I'm going to choose that first option. I'm going to hit enter again. So we get 10/231. All right, any questions about B? And then the last one says a white pencil, another white pencil, and then a yellow. Okay, a white pencil, another white, then a yellow. Okay, so I'm going to use the fundamental principle of counting, but this instance we're going to use 3 probabilities, right? For the first pencil, second pencil, third pencil. So the probability that the first pencil is white, so we're going to start with 22 pencils in the bag. And to start with, there are 6 white pencils. So the probability that the first pencil is white is 6/22. For my second pencil, we've taken 1 away, so the denominator or the total number in pencils in the bag changes, right, from 22 to 21. Also, the number of white pencils changed because we've taken 1 away. So now we have a choice of 5 white pencils. For our third pencil choice, we're going to reduce the number of pencils by 1, right? So we now have 20 pencils to choose from. And out of those 20 pencils, how many are white? Still 11, right? And so we're going to multiply the numerators, multiply the denominators, convert it to a fraction, or excuse me, convert it to a decimal, and then convert that decimal to a simplified fraction. All right, so in the numerator, we have 6 times 5 times 11, which is 330. In the denominator, we have 22 times 21 times 20, which is 9,240. I'm going to divide 330 by 9,240. And if we round this to 3 decimal places, in my third decimal place, I have a 5. I'm going to look one number to the right. Since that number is 5 or higher, I'm going to round the 5 up to a 6. So it's going to be 0.036 as a decimal. Notice when I'm changing this thing to a fraction, however, I'm not using this rounded number. All right, I'm just using the true value that's stored in the calculator. So now if I'm going to convert this to a simplified fraction, I'm going to hit math. I'm going to choose the first option, and we have 1 over 28. All right, and all of those seem to be very low percentages. All right, any questions about number 8?
Will it have like a problem where it'll be like a white pencil and then 2 more white pencils and then a yellow, like where it's more like pulling out more than one in the problem?
Well, if that were the case, you would still use this same like scenario. Mm-hmm. So like when you still multiply the probabilities, you would just take into account your total, your baseline total, and then you also take into account the number of pencils that are left in the bag. Okay. So that's almost like it's a different way to ask the same question, so to speak. So sort of similar to the marble thing, where you reach in and grab 2 marbles at once. That example and these examples have the same principles. The only difference is you're not reaching in the bag and, let's say, grabbing 2 pencils at a time. Right? So it's like the same concept, but just delivered differently. All right, now we're going to take a look at number 9. We're going to take a look at this one together. And it says that a study reports that 63% of the residents of Mississippi refuse to pump their own gas. Now, I don't know how true this is. I mean, I've been in Mississippi, but you get to pump your own gas when you go to the gas station. So, all right, so it says they refuse to pump their own gas. If 4 residents are chosen at random, so here again, this is from everybody in Mississippi, so this is a large population of people. Find the following probabilities. All 4 of the randomly chosen people refuse to pump their own gas. B says none of the 4 refuse to pump their own gas. So that means they're pumping their own gas. C says at least 1 of the 4 people refuse to pump their own gas. So we're going to take a look at these one at a time, and then we're going to see how one of the answers, we have to use that answer to calculate another probability. Okay. So first, let's look at the first one. All 4, this is A, all 4 refuse to pump gas. All right, so I'm just going to map this out with the first selected person, second, the third, and the fourth selected persons. Right? So now keep in mind that these events are independent because we got a large population of people. So what is the probability that all four refuse to pump their own gas? Well, for the first person that you choose, what's their probability of refusing to pump their own gas? Should be 63%, right? So 63% as a decimal is 0.63, right? The probability that the second person refuses to pump their gas should also be what? That same probability. And it should be the same for the third and the same for the fourth person, right? So that's 0.63 raised to the fourth power. And that gives us a probability of 0.63 raised to the fourth power. 0.158. All right, because I'm rounding to 3 decimal places. I look at the third decimal place as a 7. I look 1 decimal place to the right. Since that's 5 or higher, I round that 7 up to an 8. All right, so that's A. B says none of the 4 people refuse to pump gas. So I'm going to map out 4 people using the fundamental principle of counting. So now what I'm given is the percentage of people that refuse to pump their own gas. This is asking me for the probability that none of these people refuse to pump gas. So if I go back up to the probability for the people that refuse to pump gas. So if the total population is 100%, 63% refuse to pump their own gas. So the other percentage, right, that's subtracted from 100, that would give you the population of people who pump their own gas, right? So what would that percentage be? 37%, right? Let me just kind of map this out over here. So 63% refuse to pump gas. So that means that 37% pump gas, right? So all together, that gives you 100%, which would be the 100% of the residents of Mississippi. So now I'm going to use that 37%. So for B, it says none of the 4 people refuse to pump their own gas. So what's the probability that the first selected person pumps their own gas? Well, it would be 37%, right? The probability that the second person pumps their own gas would have that same probability, right? Because these are independent events. So the probability would be the same for the third and the fourth. Right? So the probability for all 4 of these people would be 0.37. All right, so we can take 0.37, raise that to the 4th power, and we have 0.019. Right, I'm rounding that to 3 decimal places. 0.019. So any questions about B? So they kind of faked this out. They gave us one probability, but we actually had to use what's called the complement. Right? We subtracted 63% from 100% to get the 37%, and that would represent the population of residents in Mississippi that pump their own gas. They don't refuse. They'll just go ahead and pump it, right? So a probability of choosing 4 people as such is 0.019. Now here's the third one. Whenever you see the probability of at least one, this is equal to 1 minus the probability of none. So whenever you see the probability of at least one, that's equal to 1 minus the probability of none. So like I alluded to, we're going to have to use a previous calculation to figure this one out, right? So what's going to be the probability of at least one? Well, it's going to be 1 minus the probability of none. So what is the probability of none? That's going to be the percentage we got from part B, right? Because B says that none of the 4 refuse to pump their gas, which is 0.0187 or 0.019. So whenever you're asked to find the probability of at least one, the first thing you have to do is find the probability of none. So we found that in a previous calculation, which was 0.019. And now if we subtract the two, 1 minus 0.019, we get 0.981. So the probability that at least one person of the 4 that refuse to pump gas is 0.981.